In the present video, we will discuss the example problem on ranked positional weight method. Let's see the problem. 12 tasks with times and precedence requirements as shown in the following table are to be assigned to workstations using a cycle time of 1.5 minutes. So here given the table for the various tasks, that is the task is A to L, 12 tasks are given, and also given the its processing time, that is the length in minutes, and also given the immediate predecessor. Then you have to determine the draw the precedence diagram for this line and compute the percentage of ideal time and efficiency according to ranked positional weight or RPW method. So here given the cycle time, that is the 1.5 minutes. So let's see the solution. First we have to draw the precedence diagram for the given line. So in the table you have to observe for the task A and the task E. So there is the no immediate predecessor, which means these activities or this task are the starting task. So I have to start with the task A and task E. So task A length is the 0.1 minutes. Similarly, task E time also 0.1 minutes. So next we have to go for the task B. For the task B, immediate predecessor is the A. So after completion of the A, immediately B will be start. And its processing time is the 0.2 minutes. Next is the for the task C, it will be start after completion of the B. So after completion of the B, immediately C will be start and its processing time is the 0.9 minutes. And next for the task D, so task D will be start after completion of the C. So after completion of the C, we have to draw the task D and its processing time is the 0.6 minutes. So E already we draw that one, task E. Next we have to move to the task F. Task F will be start after completion of the D and E. So after the D and E, F will be start. So have to draw the task F like this. So which means it will be start after completion of the D and E. Next one is the task G. So task G, immediate predecessor is the F. So after the F, G will be start and its time is the 0.4 minutes. Next is the task H. So task H will be start after the G and its processing time is the 0.1. Next is the task I. It will be start after the H and its time is the 0.2. And next is the task J. It will be start after the task I and its time is the 0.7 minutes. Next one is the K. It will be start after the J and its time is the 0.3 minutes. And last one is the L. It will be start after the K and its time is the 0.2 minutes. So this is the precedence diagram for the given line. So next we have to calculate the percentage of ideal time and efficiency according to the RPW method. So in the ranked positional weight method, for each work element we have to determine the positional weight. And positional weight is the total time on the longest path from the beginning of the operation to the last operation of the network. So first we have to determine the positional weight for the task A. For the task A, longest path, so here possibility of the path is only one path only, that is, so A to B, C, D, F, G, H, I, J, KL. And its positional weight is the 0.1 plus 0.2 plus 0.9 plus 0.6 plus 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. So its positional weight is the 3.9. So next we have to move to the next task. So for the task B, so longest path will become the BC DF GHI JKL, and its positional weight will become the 0.2 plus 0.9 plus 0.6 plus 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. So it is the 3.8. So positional weight of the B is 3.8. So next we have to look for the task C. For the task C, longest path will become the CDFG HIJKL, and its positional weight is the 0.9 plus 0.6 plus 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. It is the 3.6. So next to task is the D, and its longest path is the DFGHIJKL, and its positional weight is the 0.6 plus 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. So it is the 2.7. Next to task is the E. For the E, longest path is the EFGHIJKL, and its positional weight is the 0.1 plus 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. So it is the 2.2. And next to task is the F. For the F, longest path is the FGHIJKL, and its positional weight is the 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. So it is the 2.1. So next we have to move to the next task G. For the G, longest path is the GHIJKL, and its positional weight is the 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2, and it is the 1.9. Next for the task H, so longest path is the HIJKL, and its positional weight is the 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2. It is the 1.5. So next to task is the I. So for the I, positional weight is the 0.2 plus 0.7 plus 0.3 plus 0.2. It is the 1.4. Next for the task J. For the task J, positional weight is the 0.7 plus 0.3 plus 0.2, which is the 1.2. So next for the task K, so positional weight is the 0.3 plus 0.2, which is the 0.5. And last one is the next for the task L, positional weight is the 0.2. So next we have to rank the work elements in descending order of ranked positional weight, beginning with the work element with the highest positional weight down to the one with the smallest positional weight. So we have to write down in the descending order of the ranked positional weight. Based on that one, I have to give the rank. So for the highest RPW value, I have to give the first rank. Like that, in the descending order of the RPW value, have to give the ranks. So here, for the task A, having the RPW value highest one, 3.9, so have to give the rank 1. So next to B, 3.8 rank is the 2. Next to C, 3.6 and rank 3. And like that, so up to the L have to give the ranks. So here observe, so all the ranks are in the ascending order only, 1, 2, 3, 4 up to the 12 only. So next we have to move to the assign the work element to a station. For this, choose the highest RPW element Then select the next one. Continue till cycle time is not violated. Then follow the precedence constraint also. Continuously have to repeat the same procedure until the completion of the all the task. So for this one, draw the tabular column like this. First one is the workstation, next column task and processing time, then RPW value, cycle time and the ideal time. So I have to write down this tabular column. So first I have to start with the station 1. So in the station 1, first you have to add the task A. So if you add the task A with the processing time of the 0.1 and cycle time is the 1.5. So after adding the first task in the station 1, ideal time will become the cycle time minus its processing time, that is the 1.5. So next I have to move to the task B. So in the task B, processing time is the 0.2, but here ideal time after the task A is the 1.4 minutes. So we can be add the B also. After the adding the B, then ideal time will become the 1.4 minus its processing time is the 0.2, it is the 1.2. So next we have to move to the next task C. So its processing time is the 0.9 and available time is the 1.2. So we can be add the task C also. After adding the task C in the first station, ideal time will become the 1.2 minus 0.9, which is the 0.23. So next we have to move to the next task, that is the D. Here processing time is the 0.6 but ideal time is the 0.3 only. So in this regard we can't able to add the task D in the workstation 1. So we have to close the workstation 1, then start the workstation 2 with the task D. So in the workstation 2, we have to add the task D. So its processing time is the 0.6 and cycle time is the 1.5. So after adding the task D, ideal time will become the 0.9. So next I have to move to the task E and its processing time is the 0.1 and availability of the time is the 0.9. So we can be add the task E in the second station. Then after adding the task E, ideal time of the second station will become the 0.8. So next we have to move to the next task F. So processing time is the 0.2 and availability time is the 0.8. So we can be add the task F in workstation 2. So after that one, ideal time will become the 0.6. Next we have to move to the task G. So processing time is the 0.4 and ideal time is the 0.6. So we can be add the task G in the second workstation also. So after that one, its ideal time will become the 0.2. And next we have to move to the next task, that is the H. Processing time is the 0.1 and availability time is the 0.2. So we can be add the task H also in the station 2. Then after that one, its ideal time will become the 0.1. So next we have to move to the task J. Here processing time of the task I is the 0.2 but ideal time is the 0.1 only. So in this regard we can't able to add the task I in the second workstation. So I have to close the second workstation and start with the another new workstation, that is the third workstation. In the third workstation, first task is the I and its processing time is the 0.2. Then ideal time will become the 1.5 minus 0.2, it is the 1.3. Next task is the J. Processing time is the 0.7. Availability time is the 1.3. So we can be add the task J in the third workstation. And after adding the task J, ideal time of the third workstation will become the 0.6. So next we have to move to the next task K. Processing time is the 0.3 and availability time is the 0.6. So we can be add the task K in the third workstation. After that, so ideal time will become the 0.3. So next we have to move to the last task L. its processing time is the 0.2, but ideal time is the 0.3. So we can be add the task L in the third workstation, then ideal time is the 0.1. So this is the 3 workstation. So first workstation is with the task of the ABC, and station 2 is the task of the DEFGH. Third workstation is the task with the IJKL, and ideal time of the first workstation is the 0.3, and ideal time of the second workstation is the 0.1, and ideal time of the third workstation is the 0.1. Next we determine the line efficiency. So line efficiency equal to the sum of task times divided by actual number of workstations into workstation cycle time. So here sum of task times is the summation of the processing times of the all the task. So that is the 0.1 plus 0.2 plus 0.9 plus 0.6 plus 0.1 plus 0.2 plus 0.4 plus 0.1 plus 0.2 plus 0.7 plus 0.3 plus 0.2 divided by number of workstations are the 3 and workstation cycle time is the 1.5. Then efficiency will become the 4 divided by 4.5, which is equal to the 88.89%. So next we have to determine the balance delay, which is equal to the 1 minus efficiency, that is the 1 minus 0.8889, which is equal to the 11.11%. So this is the solution, and thank you.